Yeah, so hi, good evening, everyone. So welcome back to Plan 252. Yeah. So this is the agenda for today. We'll discuss two things. Yeah. One is the first slide is pedestrian in business. Okay. And the second is about uh, the second slide is network structure and utilization. Yeah. So in this slide, we will discuss about trajectory analysis, matrix sets, and flow, yeah, how we get the OT flow, and relationship between the network structure and network utilization automatically. Okay. I have developed three labs, yeah, is in Moodle, the links. And then at the end, you will have two assignments. Yeah. One is for the pedestrian network, and the second one is for network structure and utilization. Okay. Is this okay with you? Okay, good. I will start sharing with uh, second screen here. Okay, can you see my screen? This is the screen of Moodle. Okay. Okay, let's start with the midterm. Okay, you can go to the midterm, and then you can check your own mistake. Yeah, there is already the answer there. Okay. So then you can check on your own, yeah, why you make that mistake. But anyway, no need to worry. It is very small percentage, isn't it? In the total, you can check the course syllabus, yeah, the percentage of midterm, and I think it's like 10%. Maybe I don't know. Uh, so this is the slide that we will discuss today. Okay, and this is the paper about this slide, and then this is the assignment. Okay. And for the second part, there is a video in YouTube, about 15-minute video, so you can watch on your own. Okay. And this is the slide. And there's also text explanation about this network structure utilization. And these are the three labs. And the last one, this is the assignment. Okay. Let's start with the first one. Pedestrian in business. Okay. So can you see my slide? I, yeah. Okay. So recently I have um, one thesis from SURP, okay, proposed by someone. Okay. It seems like the the knowledge of pedestrian still in 1970s. Okay, so since 2000s already have a lot of changes, yeah, because of the new development of internet. There is also mobile phone. Okay, there is already GPS. Okay, but the way many people in search still thinking 1970s, okay, with this only macro, standard and so on, which already done actually. Yeah. So the purpose of today's lesson is to enhance you. Yeah. I hope you can be enhanced so that when you do research, yeah, so you will get better understanding. Okay. So I will start with the concept, okay, of what is called pedestrian in business. Yeah. So without realizing, sometimes you don't know that we are actually all pedestrians. No? Okay, whether we are business people, planners, or policymakers, right? We often unaware that okay, we are actually pedestrian, yeah, at some point of time, of course. Yeah. So in traditional point of view, okay, use this, of course, restricted point of view. Pedestrian is only people who walk or cross the street, isn't it? Right? But if you want to open your mind, okay, pedestrian is not only people who walk and cross the street, on the what do you call as walkway, yeah, or sidewalk. Okay, so pedestrian, if you start to think in a broader definition, is a person, okay, who move or travel on foot, okay, or use assistive device propelled by human power, okay, for mobility. So we define it based on mobility rather than, okay, based on the infrastructure. Can you see the difference? Okay, so that include people who run, right? Uh, mother with a baby stroller, yeah, or you are queuing for a movie theater or in the airport, right? That include the children in the playground, okay? That also include the children playing in the, you know, in the street, yeah, or in the sidewalk, yeah. That also include people who walk in the mall, yeah, or people who walk into the parking lot, isn't it? So when we discuss pedestrian, that will include everything that include the people, okay, or the person who move or travel on foot. Yeah, because we define it including assisted device. That means no, with the disability, yeah, with the wheelchair is also include as pedestrian. Can you see that? Okay, so and including people who wait for the bus or chickpea. Yeah, so these are also pedestrian. Yeah? So, but this is not pedestrian. Yeah, if you use bike or you use rickshaw, yeah, the rickshaw driver is pedestrian, but the becak is not pedestrian, really. Yeah. So, what is the significance of pedestrian? Number one, the most important, you and me and everyone is a pedestrian at some point of your trip. Yeah. So in fact, this is the largest group of road user. The English is so bad. Okay, they call it pedestrian means like sidewalk. Yeah. So aside, the car is number one, pedestrian is like a low class, which is not true at all, isn't it? In fact, if you look at the city, yeah, that develop, um, the walkway very nicely, okay, including Makati City, including BGC, right? You can see what make them develop is actually the pedestrian infrastructure, pedestrian network infrastructure, okay? In fact, the civilization, okay, one of the simple measure, yeah, when your city develop as a civilized city, yeah, is the existence of pedestrian network. Yeah, so walking will connect the car, public transport to destination. So from the train to the taxi, for example, okay, you need to walk, right? So from the bus stop to the destination, the same thing with the car park. Okay. So walking in for all transport mode include all socioeconomic group and all ages. So very significant. Okay. So and there are many places that actually only pedestrian can use. Yeah, inside supermarket, inside a tall building. Yeah, downtown arcade like this. Yeah, and there are a lot of proposal to create auto-free zone, okay, either temporary or permanently. Yeah. We want to have livable city, not just for car. You remember this. As urban planner, you need to think that. Okay? So now this is what make it more interesting. Yeah. if you do research in urban planning, it's not necessarily only for public infrastructure. It can be inside a supermarket, inside a hypermarket, or inside a mall, right? So as a business become more competitive, yeah. So to stay competitive in competitive advantage, you need better knowledge, yeah, about shopping behavior, yeah. So in that case, more accurate measurement on pedestrian behavior is needed. Okay. So if you still stick your mind in the public infrastructure, which is already standard, okay, something is missing there. That's 1970s. Okay. Hello. Okay. So look at this. Okay. In 1960s, yeah, some of you may heard, long time ago, yeah, parking mean business because providing parking space will attract more people to come to the shop. Okay. That's why business people are making a lot of parking lot, you know. Okay. Now I would like to state that pedestrian is actually mean business. Yeah. So pedestrian flow represent the demand for business environment. Okay. As larger pedestrian flow will contribute larger portion, for knowing about the shop and eventually buy, from the shop. Yeah. So when the pedestrians stop, okay, they are attracted to the display. Okay, they are considering about the things on that are on the display. So if you can repeat this attraction of the display by a certain group of people, okay, that represent the potential attraction, isn't it? To buy certain products that are on the display. So pedestrian flow mean business, yeah. Pedestrian stop mean attracted to the display. So these are the basic assumption behind, yeah. So the principle behind is you can see this kind of curve, yeah. So what we do now know is a common sense, yeah, correlation between the number of pedestrian, yeah, as well as the time. Okay, so people traveling around, the number of and the number of sales, yeah. So this is the pedestrian flow on the horizontal axis, and in the vertical axis is the total sales, yeah. So up to certain level of crowd, yeah. So more pedestrians, yeah, coming to the business environment, say like mall or supermarket, or, yeah. So the higher probability they will buy. Okay. So that means, what's the implication of that? That means if you can arrange your goods, yeah, in the retail layout, that means it will give you better chance for the people to look, eventually buy, isn't it? So in other words, if the customer can be guided to look around a little bit longer, okay, there is a higher chance that they will buy more. So the longer the time of the people traveling around the mall, okay, there is a higher probability that they will eventually buy. Yeah. So the same thing, the arrangement of the good in the retail layout, yeah, has been known to give chance for the people, okay, to look on and eventually to buy. Yeah. So if the customer can be guided to look around a little bit longer, yeah, you can have a higher chance they will buy. Okay. Now, traditional approach to this is counting, right? Okay. This is where the traditional approach and the modern approach, yeah. Right. So you always think in terms of flow, right, by counting the visitor or counting the vehicles, right? But there's a problem, yeah, because the flow is an aggregation, yeah. Yes, pedestrian flow means demand for business, yeah, but the newer approach, which is microscopic, yeah. So flow is macroscopic, yeah? So the newer approach, yeah, microscopic, is to track the visitor journey. Okay, so that means you will have the detailed demand over time and space. So you will create trajectories, This is the difference between modern approach and the traditional approach. In the traditional mindset is only counting. If you are still in counting, yeah, you are obsolete. That's before 2000, before mobile phone, before internet. Okay? So if you create a proposal in thesis, still doing that, that's old-fashioned. Okay? Because we already have mobile phone, we already have wireless, we already have RFID and so on. So why don't you try to use this? Isn't it? The technology. Okay? The problem is, okay, I know I have mobile phone, I have this all these videos and so on, but how are we going to use this data? Right? Your problem is you don't have the knowledge to use this data. So this is the lesson that I want to discuss today. So that you will know, okay, through trajectory, you can actually create flow and actually much more than that. Okay. Okay. So the keyword is trajectory. Okay. Trajectory means the route, the data that the shopper or the pedestrian, okay, will pass the mall. Yeah. Look at this. Okay, can I be use this not just for the pedestrian but also for the car? Yes, of course. Now we have GPS, right? So you just simply can connect the GPS of the people, then you can get all the same thing. Yeah, but pedestrian is easier because you can follow. Yeah. So now the aggregation of dynamic trajectory analysis over time. Okay, let's call this flow pattern. Yeah, that represent the attractiveness of the alley, yeah, based on the frequency of trajectory. Yeah. How many times this alley was passed? That represent the flow. Yeah, that the flow represent the demand of that alley. Is that clear? Yeah. So from trajectory, you're supposed to get the flow. Yeah. That flow represent the demand. Yeah, simple, yeah. Okay. Yeah, this study was done 2006. Yeah, in the beginning of mobile phone. Yeah, so at that time, gadget is very expensive. Okay, so and at that time we require advanced knowledge about how to use the GPS and so on. But now is practically everyone have mobile phone, isn't it? Okay, so and because at that time was still expensive, okay, I was asking, okay, but in developing countries, yeah, in like in the Philippines, you know, Indonesia, okay, the labor cost is much cheaper than the electronic device, yeah, at that time, okay. So then I was asking, can we use only questionnaire survey? Okay, many of you like questionnaire survey, isn't it? Right? So but your questionnaire survey is just asking question. That is very old style also. Okay. So I want to challenge you to use this kind of method. Yeah. That the questionnaire survey is not just asking question. Yeah. But actually to draw. Okay. So yeah, of course, better yet can we develop the device to automate the process. Yeah. So there is. So okay, the because we are using questionnaire survey, so we don't know the time, okay, the actual time, okay. Later on, I develop using mobile phone, so we can actually get the time, so the dynamic trajectory, yeah. So because we don't have the time in the questionnaire survey, what we have is called ordinal trajectory or static trajectory, okay. So the exact time is not important in the sequence, yeah. So the most important is actually the trajectory itself, the path. Can you see that? Okay, so we track the pedestrian route, the path in the business environment. Okay, the time itself is not important, only the path. Okay, assuming that the total study period time, whether the static and dynamic are the same, then of course the aggregation of the static trajectory over all time eventually will approach the same. Whether the dynamic or static will be the same if you assume the same period of time. Okay, this is the assumption behind. Okay. Now I'll give you simple tutorial. Okay, so that you can do it. Is that okay? Okay. Imagine this is a mini market. Yeah. So there is an entrance here in the right. Can you see? There is an exit in the left. Yeah. And there is a big shelf here. And there are 1, 2, 3, 4, 5 shelves, in the blue. Okay. So this is layout plan in 2-dimension top view. Okay. Can you imagine this? Yeah. So we would like to model this alley using graph theory. Okay. So what can we do? So what we can do is just to draw, maybe in the center of this two alley, something like this, the red one here. Can you see that? Yeah. So we draw this manually. Yeah. Because they're pedestrian, so two ways, right? Okay. So, and then what you will do, we will keep name, A, B, C, D, E, F until, in this example, until L, Okay. So, in this graph, that red represent the alley, So, can you see, I create a reference coordinate, The reference coordinate system is actually arbitrary. You can put on the top or the bottom, left, right, whatever. Okay, so I just choose like Euclidean coordinate system. So 0, 0 here, and then this is x on the right, and then top is y. Okay, arbitrary. You can choose any coordinate system, and then based on this coordinate system, now what I will do, I will create I can measure, right? Now I can measure so that I can draw this. So I can put A here is 12.5, 5.5. B here, this is 12.5, 7.5. Okay, this is the real measurement in the actual meter. So 5.5 is 5.5 meter from this 0, 0. 12.5 is 12.5 meter from this 0, 0. Is that okay? Yeah, you can measure using measuring tape, right? Okay. Up to here, is it clear or not? Okay, good. Now you have the real layout, and then you can create the graph, and you can get the coordinate. What is that for? So that you can get the distance. Okay, from there you can get the distance. Oh, based on the graph, the red line here, you can create the adjacency matrix. What is adjacency matrix? This is adjacency matrix of that graph, the red line there in the alley. 0 means the two vertices, 2 point has no connection. 1 means two vertices are connected. Let's see. Of course, the middle, the diagonal is 1, because it represents self-loop. The self-loop is not wrong. Pedestrian, remember. So this should be symmetric because two-way. So all you need to do is to fill up the upper part here, and then the lower part is just symmetric, equal. Okay. So let's see. You have A to B, right? There, A to B. So there is a line, so you put 1. Is it clear? Yeah. So you have also from B to D, isn't it? So can you see from B to D there? B also connected to C. Yeah. All the others are not connected, so put 0. Is it clear to create adjacency matrix from your graph a while ago? Easy or not? Easy, yeah. Good, thank you. So now, because you have the coordinate, so all the one here, you can put the distance, isn't it? Yeah. Knowing the coordinate of its vertices, you can compute the distance, isn't it? Yeah. This will create distance matrix. What is this? This is the shortest distance matrix. Yeah. So distance matrix and shortest distance matrix are not the same. Yeah. So the number of its element in the distance matrix represent the length of the link. Yeah, the connected vertices. So unconnected vertices, infinity. Yeah. But when you calculate shortest distance matrix, you will have this. Someone want to say something? A while ago.
Yeah, Prof, this is for the adjacency metric, so maybe later. But I wanted to ask, how can A be adjacent to itself? How does the self loop work?
The self loop. Okay, I will draw. Wait. The self loop is something like this. So in itself, that means from here you can go here in its loop, right? If you draw. Meaning from B, you can go back to B, right? You can turn around in the same place. Every corner, you can just go around in the same corner. That means self loop, yeah? Remember, we have
Yeah,
pedestrian, just turn around. This is not
yeah,
car.
but yeah, for roads, it's not the same, right? So you can't do AA
Yeah,
for
for the road,
roads.
it's not the same.
Okay,
Yeah?
okay, yeah,
So
okay.
for the road, you put 0 because the car cannot turn around like that in the same node. Yeah, for pedestrian can.
Okay, thank you. Sorry.
Good clarification. Yeah, thank you. Please. Yeah. And so adjacent symmetric clear. Oh, I need to delete this. Clear. Okay. Next, from the distance matrix, is it clear or not? You get the coordinate a while ago. Let's see here. Okay. So for example, from A to B, what is the distance? 2, right? See, 7.5 minus 5.5. So then you can get that down 2. You see, yeah? Okay. So now, from the distance matrix to get shorter distance matrix, this one required an algorithm. Yeah. So this required algorithm called Warshall algorithm. Can you search in Google Warshall, Fjord Warshall algorithm? Yeah. I think in one of my lab, either in IFN transport or somewhere, I already created this. So all you need just to input and then you can get all. So all you need to get is just the distance matrix and then you can get the shortest distance matrix. Yeah. So if you look at this color, red color numbers here, which is non-zero, yeah, 2, 7.5, 2.5, this is exactly the same as the distance matrix, which is in blue here. So because of course from A to B still 2, yeah. But what is the difference? Yeah, the one in blue in the shortest distance matrix represent if I want to go from A to C, okay, that distance is 9.5. So this is like the shortcut. Yeah. So it doesn't tell where to go. Okay, it just tell from A to C, the shortest is 9.5. Yeah. So you can actually confirm that in here. Yeah? From A to C, of course, you will put from A to B and then B to C, isn't it? So in that case, that's correct. Yeah. So 15 minus 5.5, so 12.5. Yeah. So of course, you can go around and then go to C. That's not shortest, right? So what we want is the shortest distance matrix. Yeah, this is can be computed. Once you have the distance matrix, you can get the shortest distance matrix. Yeah. Okay. That is in the network structure, isn't it? So we need to distinguish network structure and network utilization. Network structure means given the layout, okay, you can get the graph, the network, and then you can also measure the things from the network structure, yeah, including the adjacency matrix, the distance matrix, the shortest distance matrix, everything that related to or path matrix, yeah, related to the network structure itself, yeah. This is one part. Okay. The next part is how we utilize the network. Yeah, represent the demand. Yeah. So here, this is where you will ask your respondents. Yeah. Okay. So in your questionnaire, you draw the layout. Okay. And then you ask the respondent to draw. Okay. How do you, usually in the end, near the cashier. Okay. So we'll ask you, which way did you use this supermarket? So let them draw based on their memory. Yeah. If you don't agree with that, of course you can follow them wherever they go, right? So this is called stalking. Yeah. So we stalk the. Of course you ask their agreement. Yeah. So using stacking method, okay, you can actually get not only the path, you can also get the time, if they stop for a long time there, so you can actually record that. Yeah, in 2000, I forgot, maybe 2009, yeah, one of the students that I asked them to create a mobile phone to just record the stalking behavior. Yeah. So let's imagine this is the two pedestrian trajectories, based on the questionnaire survey. So two pedestrians, so red and blue. Is that okay? So, and the number here represent the ID, ID of pedestrian. Okay. Now we are going to discuss how to get flow from this trajectory. Okay. So number one, okay, what you will do is you put back this trajectory into the graph. Okay. Long time ago in 2013 or 2014, I have this project with the UST, the same, but for car, not for pedestrian. Okay, so we connect with the GPS of taxis, okay, and then we track their GPS, okay, and then we can get the trajectory of the taxis. Yeah. And then what we will do, we project the trajectory in each road because the road network is already graphed. Is it clear or not? Yeah, so that's application for the vehicles. Yeah. For now, let's come back to pedestrian so that this is the simple version. Yeah, so you can understand the whole concept. Okay, so what you will do, this one, red and blue, are drawing of the respondent, isn't it? So then manually, you need to get the actual trajectory in terms of the graph. Okay, can you see this? So A, B, C, D, that. Yeah, I deliberately make it difficult for you in the red because it's come back. So can you see from E, okay, even though only halfway, I put it until D. Yeah. Because otherwise you need to put another point here. Yeah, maybe E1 or E0, whatever. Okay. Without that, you cannot represent the trajectory correctly. Yeah. It is a simplification. Yes, Justin.
Sir, question. For
Mhm.
example, a person goes around at a node like a self loop. Do we have to double the trajectory, the path?
Self-loop means you are turning around in the same point.
So, yeah. So, for example, for the red trajectory, let's say
Mm.
A, B, but at node B, he decided to rotate. Do we have to write it as ABB or just AB?
So, okay, good question. Yeah. So in B, it just turned around. Okay. But because this is static trajectory, not dynamic. Okay. So you don't really need to put it BB, right? Okay. But if you want to put it more dynamic, yeah, that means you need to record also the time. Okay.
Okay, sir. Yeah, thank you.
Okay. So let's distinguish between static trajectory and dynamic trajectory. In static trajectory, you only record the path. In dynamic trajectory, okay, you will record also the time. Okay. So when people turn around in the same place for a long time, you don't need to record that in static trajectory. But in dynamic, when you record the time, automatically it's recorded. Okay. So look at this. There are a lot of possible potential research, yeah, in this area, which is still untouched. Sayang naman, right? So, and the point is, you keep doing the research in 1970s knowledge, which is shameful. Okay? So I want to criticize harshly because keep doing the same obsolete research in 2025. Okay. So now this is example, so I'm using Excel. Okay, so what we are doing is I created this pedestrian number 1 and 2, okay, because I already have this trajectory, yeah, A, B, C, E, D, right? This one, so I will put it there. Exactly. This is typed manually, yeah, these two pedestrian trajectory. Is it clear? Huh? So we input its label of the vertex sequence into a cell in the Excel, yeah, spreadsheet. Yeah. So then we can use this information to compute the flow count, and then later the alley attractiveness index, yeah, in the same spreadsheet. Okay, let us see. Number one, of course, you need to check, yeah, whether this trajectory is already in graph or not. This is very important. Yeah. So I have put this using function, Excel function, is number or not. Okay, and then matching or not. Yeah. So this is the function I put here. Can you see? Yeah. So you can also combine later using concat. Yeah. This is a function, built-in function in Excel. Yeah. So, and later you can use and. So once you create this, whether this is in the, oh, how to get the link? Link is just consecutive, right? If you have A and B, so you create AB. This is concat. You see? So B and C, so you get BC. That is concat. Yeah, concat of the two strings. So you get the links. Yeah, and then you check whether this link is actually in the trajectory or not. Yeah, this is the trajectory. Yeah, so I put it there. Okay, and then this is the link. Okay, and then you check whether this link here is represented there in the link of trajectory. So if yes, it will be say true. And then what you will do, if this is trajectory on graph, then there is no false. All must be true, right? So there, this is the final result, yeah, the green one. Yeah, that all of these, yeah, must be true. Then this trajectory is on graph. Is this clear or not? Yeah. So once you have the trajectory on graph, okay, that's the first check. Then you can count. Yeah. So I put it back here in this cells. So per trajectory. Yeah. So then you can count in the total. Yeah. Count if they are true. Yeah. So yeah. So to do that, yeah, we use the match function. Yeah. Match function basically return the index position, yeah, of the match label. Yeah. If unmatched, it will return NA, yeah, not available. So to avoid that, we probably need to use ISNA, yeah, is NA. So basically, what we are doing is to compute every possible edges, yeah, in each direction, and then combine both direction, yeah, to get the total flow here. Of course, this is only two trajectories, so very simple tutorial. So you will get this at the end, yeah, total flow here. Can you see? Yeah. So based on this total flow, okay, then what you will do, you put it into, yeah, flow matrix. Yeah, and then you can draw. Yeah, this simple. Yeah, you replace the 1 in the adjacency matrix here, not include the diagonal. Okay, with the flow, and with the total flow. Okay, so you get this pattern, yeah, flow pattern, right? And then you can draw with the thickness in the arrow here. Is it clear or not? Simple, yeah. So you get trajectory to flow. You see, yeah? Any question? Any question? So the result, okay, will be flow pattern. Yeah, so when we draw the count of each flow pattern in each alley into that graph, yeah, and then you scale, yeah, the graph according to that flow pattern, you have this figure. Okay? So this figure represents the alley attractiveness. Yeah, of course, the thicker, yeah, represent more flow in that alley. Yeah. So it is true. It doesn't represent the actual flow or the density. Yeah. Okay. Because we don't really want to get the real flow. We are taking sample here. Remember. Huh? So what we want is actually the relative flow, isn't it? So alley attractiveness index represent the relative flow, yeah, of the alley. So this information is very useful, yeah, to distinguish which alley on the store will get more flow than the others, right? And then later what you will do, you do cross tab, yeah, cross tabulation. So you relate this flow pattern with the product that they are selling on that alley. Okay, so and then the next step is what will happen if they change the layout? What will happen if they rearrange the goods inside the store, right? And then what the trajectory movement will change, These are the beautiful and interesting studies. Yeah. So of course, again, yeah, the longer they will move around, the higher probability that they will buy, right? That's the main principle there. Okay. Now, once you have the adjacency matrix, you get the flow matrix. Yeah. So this is the result of the flow matrix. Okay. And this is the graph, yeah, the allele attractiveness index, isn't it? Oh, it is only 2 pedestrians, and that does mean there isn't zero. Yeah, nobody is passing this alley. Yeah, because we are only 2 pedestrians. Yeah? The sample is not enough. Okay. So what is allele attractiveness index? Is just the relative flow. Yeah. So you can simply take the flow pattern divided by the maximum. Okay. With this, you will get the number, the index, which is from 0 to 1. Yeah, it's like probability, you know. So what is the point here? You localize the problem in the supermarket. Yeah. So rather than getting the absolute value of the flow pattern, okay, now you get localized. Yeah, the flow pattern is actually absolute value. Allele attractiveness index is the local information. Yeah, that you can use to compare. Yeah, within the same supermarket, of course. Now I want to show you, okay, the real world case study. Yeah, has been done in 2008, 2007 to 2009. Yeah. Yeah. I was in Vienna in Austria at that time. So one of my student in Indonesia, yeah, doing this study. Okay. So we only use online advisory. Yeah. At that time there is no Zoom, yeah? Only email. Okay. So yeah, this is a supermarket in Surabaya. Okay, and I asked him to do just one person, undergrad, okay, civil engineering. So I asked him to do inventory survey first. Okay, and then we developed the questionnaire survey, 2 part. Yeah, one is the trajectory of each shopper in that hypermarket, and then of course the shopping behavior. Yeah, which is more on the socioeconomic activity in the mall and shopping trip and so on. Yeah. So what I want to discuss is only the first part. Yeah, the shopping behavior is related only to that study. Yeah. So this is the inventory survey. He did pretty well, very detailed. Can you see? Okay. And this is the shelf that's selling rice in the back. Yeah. These are the appliance. Yeah. These are the cafeteria. Okay. There is AMW there. Yeah, music shop. So it's quite big. Yeah. The hypermart is quite big. There are many shop inside also. And these are the entry and exit, and the trolley are here. There's an ATM machine there. Okay. And fast, fresh food are in the back here. Yeah. And the one in the area divided by the category. Yeah. This is grocery, stationery, yeah, beauty, clothes, and so on. Okay. Electronics. So it's just like in SM. Yeah. Department store. Okay. So, and this is the example of one trajectory. Yeah. So that drawn by the respondents. Yeah, the blue one. Yeah. So there is a turning around here, and you see. Yeah. So this is the real trajectory drawn by the respondents. Yeah. And okay, this is the structure of the study. Yeah. So we get the layout a while ago. Okay. And we get also the data, which is the static trajectory. Okay. The same step, yeah, like the tutorial a while ago. So we draw the network graph, we compute the distance matrix, and then compute the shortest path, yeah, or shortest path matrix. Yeah. From there you can get the statistic, right? So from this distance matrix, you can get the statistic of walking distance, yeah? Also the flow pattern, right? And alley attractiveness index. From there, okay, now we combine the utilization and the actual utilization, the walking distance, and the shortest path. Okay, I don't like mean, so I like median because median is very robust. Okay? So we get the median ratio, yeah, and then we compare with the shop inventory a while ago. Okay, and then we will get the product spatial preference. So this is business intelligence practically, yeah, on the move. Yeah, remember this is study 2006 and 2007 until 2009. Okay, so this is the sample, the graph model of the array. Total node is 88 nodes. Okay, manually, this student doing it manually. Okay, 139 links. Yeah. All two ways except here in the cashier. So the one in the 1C, 1D, 1E, and so on, these are the cashier. Yeah, until here. Can you see? And these are the coordinate, yeah, that he tried to get. Okay. And once we have that, exactly the same method, okay, we can calculate the distance matrix. Yeah, these are the pattern. Yeah, I've used MATLAB to get this distance matrix. Oh, this is non-symmetric. Yeah. Why? Because there is one way. In the cashier, there is one way. Okay. So that's why non-symmetric. Yeah, these are represent the blue and all color here represent the non-symmetric because of the one way. Yeah. And this distance matrix, I put it into infinity. That infinity means there is no connectivity, right, between the two nodes. Yeah. And look at this. This is only the small part here. The pattern here is 88 by 88. So I have only a few pattern here that I zoom in, yeah, into Excel. Yeah. Okay. And then this one we compute using Fjord-Warshall algorithm. Yeah, that's all shortest path. Yeah. Again, we can zoom in this part. So the earlier distance matrix is a lot of infinity. Now we get full, yeah, except the diagonal. Yeah. Is it clear up to here? So once you have the all shortest path, okay, then what you will do, you can get the median. Yeah. Okay. So the median, you can get the statistic practically. Yeah. You can draw the distribution of all shortest path. Okay. It's not normally distributed. It's shifted toward the left. Okay. And these are the statistics. Yeah. The mean, median, mode, maximum, IQR, skewness, and so on. So that is a outlier also. So we can get the outlier detection using this block spot yeah, method. Can you see that? Say this is network structure, right? Yeah. So based on only network structure, yeah, no utilization. Okay, we can get already the statistic. Yeah, interesting. Next, now how about the utilization? Yeah. So again, we need to put it one by one. Yeah, for all pedestrian. Yeah, this is pedestrian number 160. Yeah. So we need to put the trajectory in terms of graph. Is it clear? So 1A, B, D, F, these are the part in the graph. Yeah. So from the drawing, yeah, of the respondent, you need to put it into the actual graph so that we can put it into computer. Otherwise, you cannot compute, right? So next, once you put into graph, you can calculate the walking distance, the real walking distance. Okay, and then you can compare. Yeah? Oh, interesting. Yeah, even though it's just drawing, yeah, interesting, yeah, almost normal distribution, yeah. Which is correct, right? The walking distance is about normal distribution, and these are the statistics. Yeah? We only gather 188, actually more than that, but there are many samples that is actually not correct, so we ignore. Yeah, I think 200 plus, but we remove, yeah, some of the sample that is incorrect. Okay, so only 188 is valid. Okay, so these are the numbers, and then if you compare the median, this is interesting, no? Yeah, if you compare the median, so I get the median ratio, 7 times. So the actual walking distance is 7 times longer than the ideal shortest path. Yeah. At that time, there was a literature in Britain, I think by someone in the UK, telling that pedestrians tend to walk in shortest path. Well, that's true for maybe if they want to go to work or they want to go, yeah, for certain things that they want to walk fast. Yeah. But in shopping, it's totally the other way around, right? People want to walk longer than shortest path. Yeah. Interesting. Yeah. So how much longer? More than 7 times. So we can actually get the number. Yeah. Yeah. This is in Surabaya. Maybe you can get different value in different mall. Yeah. So you can repeat the same study with different technique. Yeah. So and this is quantifiable verification, yeah, of the common sense. Yeah. Yes, we know this. Yeah. Common sense, right? Shopping is always longer, than the shortest path. Yes, but how much longer? Or when we can actually do this kind of study. Yeah, interesting part. Yeah. So now we get the flow pattern. Yeah. So based on that flow, we get actually the actual flow here. Yeah. And from that flow pattern, what we will do, we draw. Yeah. And this is very interesting. Can you see? Yeah, I put different color and thickness here so that you can see. Okay. Oh, people love to buy bakery there. Yeah. Okay. And this one is clear because this is queuing for the cashier, right? So in this bottom line here. And this one also clear because this is the main alley. Okay. Apparently they don't go in the back, and they go directly here in the middle, mostly. This is very interesting, yeah. And another interesting part here is their clothing, yeah. The sock, t-shirt, shoes, okay. Very low customers, okay. They are losing customers, especially the way they put is in front, but nobody is going here, so mostly going to the bakery, yeah. Interesting, right? So once you put the actual flow pattern and then you put it into the inventory, you do the cross tabulation, and you start to see many different patterns, yeah, that you did not see before. Can you see that? So yes, the area vertical in that, okay, the distribution is something like this, yeah, that with a lot of outliers, yeah. So this is the final result, right? So there is a correlation, yeah, between the area attractiveness index and the shop inventory, right? So the main major route, yeah, to the items, to the shopper, or what is the actually they buy. Okay, there is also low area attractiveness index, okay, with this daily usage, yeah, non-daily usage, yeah. For example, rice cooker, mixer, yeah, electronic products, yeah, clothes, bed cover, and so on. So you will know, okay, based on this kind of very simple study, can be repeated different time, different layout, arrangement, and so on. Okay. So the point is very simple method. Yeah. Only from questionnaire. You love questionnaire, so I give you questionnaire. Okay. And then you just analyze, okay, not counting, but what? Trajectory. Yeah. So based on the trajectory, then you can get this conclusion. Yes, Dennis.
Sir, does it have a gender data?
Hmm?
The pattern between male and female
Oh,
shoppers?
there is, yes, but I did not include in this. The actual study is much deeper than that. Right? There is a shopping behavior and so on. So if you want, you can contact the university for the full thesis, but they are in Indonesia.
Oh, thank you, sir.
Yeah. So the normal study, the shopping behavior, they are normal. So these are repetitive study, so that is not really innovative. Yeah? Okay. So just a regular study. So yeah, if you are interested that. Anyway, this shopping hypermart is already closed, so unfortunately. Yeah. Yeah. And the conclusion still remain the same. So walking distance, the actual walking distance is about 7 times longer than the ideal shortest path. Yeah. So that means the shopper do not walk in the shortest path. Yeah. And if you look at the walking distance inside the hypermart, which is 78 meters, and below, or above 450 meters. Yeah. So this is considered outliers. So you can actually measure the actual walking distance based on this kind of graph. Remember this, yeah. Trajectory is very rich. Okay. In fact, if I'm allowed to create a laboratory, I will name it trajectory lab, because this is very, very important things. Okay, now I want to connect this with IFN. So the next one. Okay, why this is important? Okay, I want to show you that we can actually create a self-correction. The IFN will do self-correction. So this is the continuation of above study. So IFN was discovered 2014. So this is much later. Okay, so we have full knowledge of the real world flow matrix a while ago, right? Yeah. So based on pedestrian trajectory that we have. Okay. So was done via questionnaire survey in 2009. Okay. Now, this full network flow, is estimate from here. You're supposed to be able to compute the probability parameter in each intersection, right? And then you're supposed to recover the relative flow across the network. Okay. So, and the purpose of this new study is about calibrating IFN without capacity matrix. Remember when you study IFN last time, okay, we need to have capacity matrix, right? And then you take the proportional of that capacity matrix. Okay. So in here, I want to demonstrate that IFN can be calibrated only with the real flow data. No need to predefine capacity. And the main part here, I want to introduce self-recovery. Okay. So we will show that the network naturally restores the balance through flow conservation. Okay. And I want to introduce you with the cloud nodes. That's the main point here. So the real world significance, it applied to human movement, right? The hypermarket and so on. So, and then you can start to see that we can apply this for many others. Okay. Why the node conservation flow is significant? Because this is a very reasonable assumption. Because in reality, people will travel to a place and then return home, right? But the flow is just the summation of the trajectory of the route of the people in the network. So there is no people that disappear or created when they travel, right? So that means the flow must be conserved in all nodes. That's important to be realized now. So the challenge, yeah, that network earlier, there is something one way, right? So the network is not irreducible, yeah, not strongly connected. That's first challenge. Second, the network is without capacity. So in that case, you want to create AFN, how can? You don't have the capacity. It doesn't work here. Okay? And the flow matrix is clearly not pragmatic. Okay. So, and then we need to find a way how to calibrate the ideal flow, yeah, based on the link flow from the data. This is the main part of this study. Yeah. Yeah, very simple study, but mostly theoretical. Yeah. So, to match the FN with the link flow, yeah, I need stochastic matrix. Yeah. But at that time of this study, I did not know how to derive stochastic matrix from the flow matrix, which now we know very easy. Yeah, it's just a sum and then divide by the sum. Okay, but it was a real world challenge, especially the network is reducible and non-pragmatic matrix. Okay, so in that paper, so I dive into ideal flow in the hypermarket alley, yeah, and then I will introduce self-recovery. Yeah, I will show you later. Yeah, after many trial and error using pen and paper, yeah, I suddenly discover a simple formula that solve these two problems, yeah, at once. Okay, making the network irreducible and the flow matrix become pragmatic. Yeah, at that moment changed everything. Okay, what is that? Here. Okay, real world problem often has basin, right? Have source or signal. Yeah, like the challenge a while ago. Yeah, hypermart. So how to make it from reducible network to be irreducible? Yeah, from weakly connected to become strongly connected. Yeah. So here is my technique. Yeah. So my theorem is there is only one cloud in the system is needed. Okay, so only one cloud in the system. Okay, then every sink basin has a dummy arrow to the cloud, and then every source basin have a dummy arrow from the cloud. Okay, and then the amount of flow from the dummy arrow is exactly the same as the amount of flow, yeah, that flow into the source basin or out of the sink basin. Yeah. So in the matrix, yeah, our agreement is to put the cloud node in the last node, yeah, usually in the most right column or the bottom row, yeah, of the adjacency matrix. So we add new row or new columns. Okay, and we put this as cloud node. Okay, using this, okay, suddenly you solve the irreducible problem. Yeah. So by connecting the sink basin to the cloud and then back to the source basin, we solve the network structure problem. Okay. So you can try. You can try to draw any network which is weakly connected. Okay. You want me to give you an example? So I will draw here. I will put 4 nodes. Going there, going there, going there, going there, going there. So this is weakly connected, isn't it? Why? Because there is a source here, right? And there is a sink here, right? So let's draw differently now. What will happen is now you create a new cloud node. Only one is needed. Okay. And then what you will do is you create a dummy link, yeah, to this cloud node. And then from the cloud node, you create a dummy link to the source. Now the network become strongly connected. Is it clear or not? Okay. So once you can create the strongly connected network, okay. So, oops. Okay. The next problem is how to make the flow matrix pre-matching. Right? So I found out that if the network is already irreducible, yeah, and we keep the node conservation flow, okay, it's automatic, yeah. All you need to do is just divide the flow divided by the sum of flow in each row. Yeah, you can get the stochastic matrix. And if the network is not strongly connected, that will be wrong. Okay. So we solve two problems using just one technique here. Just add the cloud node and connect it. Okay. Is there any question up to here? Is it clear or not? Okay. Now, once you have that, okay, then we can get the pre-magic matrix. Yeah. So, meaning pre-magic means total inflow in each node is equal to the total outflow. Yeah. So then again, once you make this, you still need to check. Yeah, in the real data, you need to check whether it's incorrectly summed or not. Yeah. So if there is a incorrect, so you need to correct that. Yeah. And sometimes in the computation, if there's a negative flow, that means the link direction is actually reversed. Okay, so if you get negative flow, that you need to reverse the direction. Okay, so I get that simple correction. Okay, after correcting all the flow, including the dummy and cloud node, we get the pre-magic matrix. Yeah, so using this pre-magic matrix, you will see, yeah, this is the real world flow pattern. Can you see in the right, left, and the ideal flow? Are they almost the same? Yes, almost the same. Yeah. So the overall pattern remain consistent. Yeah. Even the color is almost the same. So confirming that the model is actually reliable enough. Okay. And then I compare the ideal flow, okay, under different scaling, okay, with the real world. And of course, they are quite good in general, okay. But comparing between total flow and maximum flow scaling, yeah, apparently the total flow scaling produce closer match, yeah, than maximum flow scaling. Yeah. So this is the nitty-gritty detail on that. Okay, this is the main part. Yeah. Can you see? This is the actual flow on the left, and the right one is the ideal flow. What's the difference? The main difference is here. Yeah. Why? Because the cloud node is down there, man. So the total inflow must be the same as total outflow, which is not represented in the actual data. Right? But based on ideal flow, you do self-correction by itself automatically. Okay. So yeah. In the real world, yeah, this is the highlight, yeah, the powerful moments, yeah, of this study. Yeah. Okay. One of my students missed recording the flow at the exit door. Yeah. So which caused the mismatch. And that's done a while ago. So, but when we apply ideal flow model, yeah, the system will correct itself automatically. Yeah, this is the beauty of pre-matching property, right? So it will enforce the flow conservation without manual intervention. Yeah. And it was surprising and elegant solution that validated the overall strength of the model. Okay. Now, once we have the ideal flow, yeah, we can scale the network, yeah, in 2 ways, yeah, matching the maximum flow on the specific link or matching the total flow across the network. Yeah. So the second method is actually more meaningful, yeah, because it aligns with the average flow of the model. Okay. Visually, we saw how the links, yeah, in that 1C and 1B enlarge its value to the actual correct movement. Yeah. So this is a clear sign of self-recovery. Yeah. So in conclusion, if you use IFN, yeah, on top of that real world study, okay, it enables automatic correction of the flow inconsistency. Yeah. So that's the main part here. From unnoticed data error, yeah, to flow imbalance, yeah, the system will correct itself. Why it corrects itself? Because of the pre-magic nature of the IFN. Okay. So it has ability to scale, yeah, by the total flow, yeah, to preserve the realistic distribution, yeah, which is very powerful. Yeah. So now look at this way. Yeah. We begin with the challenge, yeah, that turn into discovery, yeah, that the network is actually can restore itself. Yeah. This is the essence of the self-recovery. Yeah, it is very beautiful and simple. So now there are a lot of further studies if you want. Yeah. So which alley actually can on the storm more flow than the others, how the design, the layout will produce better arrangement and so on. Yeah. So and then you can connect with the queuing and so on if you want. Yeah. And correlation with the rental fee, for example, of the each alley. Yeah. So this is what the business owner want usually. Yeah. So this is the similar study in the center of London, I think. Yeah. They use similar pedestrian studies. Yeah. Yeah. So and then I continue this kind of study. We developed the technique using machine learning. Okay, we put it into pedestrian. Okay, to recognize, yeah, whether they are in the stair or walking, or they are disabled, or they are using in the bus, and so on. So we can recognize the actual pattern, yeah, based on the accelerometer of the mobile phone. Okay, we can actually do that also. Yeah. So how long they will spend in certain location and what type of people using certain facilities and so on. So you can continue if you want, yeah, different activities, different methods. So there are a lot of wearable sensing device that actually we can use to recognize this. Yeah. Okay. So you can also connect it to airport control or public transport control and so, yeah. So, any question so far with this pedestrian in business? Clear. So yes, please.
Hi, sir. I wanted to ask about sampling
So,
for what is a meaningful sample for
there are sampling. So sampling depends on the sampling method that you want. Okay. And depends on the population that you want, then you will get the sampling. Say you assume the sampling distribution to be normal, then you will know what error you want, then you can get the number of samples. I think this is pretty standard, so you can get from the Wikipedia what is the formula.
for our study in Cubao, since we're doing pedestrians,
Okay.
and then a rush hour, I'm just thinking about what kind of sample that we're going to have. And just that's the context of my question.
Yeah. So I was thinking, as long as you can capture the peak hour, for example, yeah,
Okay.
yeah. So that will be sufficient in your case. Yeah. But if you want to be very valid study for the real, not for the class, yeah, for the real project, of course, you need to get it deeper than
Mm,
that sample. Yeah.
okay. Thank
Okay.
you.
Okay. So for the class, it's sufficient just you can get just simple data. Yeah. But remember, you can not just counting, that's the main point. Yeah. Get trajectory instead of counting. Yeah. So to make you feel what is this study, so I give you the assignment. Yeah, there. This is just exact copy. Yeah. So by next week, I hope this is very simple, just exactly the same like the tutorial. Okay. And I put that paper there in Moodle. Okay, so you can also download if you want. Yeah, if you are interested. Okay, so up to this point, is there any question, discussion about this topic on pedestrian? So here is the sample, I guess, of the two. And that Excel. I will move it here. So this is the Excel file with only two pedestrian. Yeah, this is only two pedestrian. Yeah, this is similar to your assignment. Yeah, so we draw the layout, okay, and get the distance matrix. This is manual. Yeah, and then get the index coordinate and so on. And then you get the flow pattern. Yeah, this is like your assignment, and which only have two pedestrian. So, any question? Yes, Justin.
Sir, for the shortest distance matrix, do we have to apply the Floyd Marshall?
Actually, if only few, you can calculate by hand that one.
Okay, okay.
Huh? This one I put it manual. Okay, this one I calculate. Oh, there I calculate manually.
Okay, sir.
Huh? Can you see? It's only a few, right? Not so many. You can calculate by hand.
Okay, sir.
Yeah. If your matrix is 80 by 80, yes, yes. Don't use manual. It will take so long. Yeah. But it's only 10, 12. I think manual is easy. Yeah. Yeah, this one, see, I do it manually, this one. Okay. For the assignment, it's up to you. If you want to experience flow Masha, so you do it. Okay. That will enhance your ability. Yeah, if not, you just do manually like this. Yeah, this is for the workshop, so I asked them to do manually. Clear, yeah? Good. So let's continue with the next topic. Yeah. Okay. So the next topic it's actually continuation of this, and that's why I put it in the same lecture. Okay. Can you see my slide? Okay. So, question now. Once you have the trajectory, okay, can we derive anything more than that flow? Can you derive, for example, OD matrix, origin destination matrix? Can you derive, for example, turning distribution matrix? Now, and then can you connect, yeah, this flow and OD and so on? This one become good question, yeah. So it started 2009 when I was going to that conference, yeah, went to Hong Kong and in the airplane, so I got the idea and continuing this study that I supposed to present the pedestrian a while ago. Okay. And from there we got this another paper, actually more than one paper, many, but the main one I will put here. So let's discuss what we will do discussion in this slide is about trajectory. Again, I will continue the static trajectory on graph. Okay. And we go deeper into network structure and network utilization and its relationship. Okay. Okay. So now let's start with trajectory. Yeah. So what is trajectory? So trajectory is defined as sequence of points, okay, over time and space. Okay, so the term space here is not necessarily physical space. Okay, can be feature space, meaning variables, any variable. Okay, so trajectory represents the path of moving agent within specified observation time period. Okay, so the time can be discrete, can be continuous. Yeah? The space can be discrete, can be continuous. Yeah, it's not necessarily physical space. I say. Yeah, later we'll see that we can put it very general. In fact, in the past 25 years, okay, this is my main study trajectory, okay, including in finance. Yeah, including the IFN start from here. Okay, including the pedestrian studies. Okay, everything is start from here. Okay, so each point, let's discuss physical space now. Yeah, each point of agent I. Okay, so agent I here in time t. Okay, in 3D physical space can be represented by this kind of vector, right? X, Y, Z, correct? Okay. So now what is agent? Yeah, in here agent is just a moving agent. Yeah, in the trajectory, yeah, depends on your context of the application. Okay, so in transportation agent usually pedestrian, maybe vehicles, maybe the goods itself. Yeah, for logistics, right? But in the tracking, so I am also doing the tracking, computer visions, yeah, say GPS trajectory. Yeah. So for example, you did cooperation with Grab, or with Uber, yeah. So you can get their trajectories data, yeah. So because they track, right, all the vehicles. So then you can get the trajectory data. Yeah. In the camera, yeah, in the each intersection and so on. So this is computer vision. So the object, meaning the vehicles that passing, this is the object ID. Yeah, that represent the agent. Hey, trajectory is not only for transport, okay? That's also in physics, yeah. So atoms that move, yeah, the molecule and so on, yeah, they are the particles. they have also trajectories. Yeah. So in biology, yeah, it's not my field, but a lot of scientists tracking the animal behavior, yeah, the bees, the dolphin, okay, including the plant's growth. Yeah, these are trajectories also. In trading, okay, each stock symbol have price, have volume, yeah. You will have closing price, opening price, high price, low price, and so on. Okay, so this represent the feature space. Can you see that now? Yeah. The space is not necessarily physical space like 3D space that you have, yeah, but can be any space. Yeah. In economic, yeah, the economy, yeah, population represent the can you track the population over time, right? In each country, in each province, in each city, including the GDP and so on. For personal management, yeah, we can use trajectory to track your sleeping schedule, your working schedule, and so on. See, application of this is tremendous. Yeah, depending on how you define trajectory, what do you define as agent, space, and so on. Can you start to see the broader definition of trajectory? Yeah, that's why I can go to different field. Yeah, not only transportation. Can you see that? Yeah, because once you create the broader definition, yeah, you can attack the same technique. You can attack from the for different field. Okay, you become more power with this. Okay, so this is an example. I track pedestrian using camera. So you can search. There is a Tecnomo Fernandez algorithm, right? So that's my name. Yeah. So this is one of them. I track this is in Japan. So pedestrian traffic on the top view, yeah, in Sendai, this one. So from there you can get the pedestrian, and I remove the background, yeah. Okay, and because trajectory in 3D space, so I'll give them name at that point, at that time in 99. So I give them name NTXYZ. Yeah, N is the ID, T is the time, XYZ is the 3D coordinate. Yeah, this is the physical trajectory, basically. Yeah. So then we track the movement of each pedestrian, one pedestrian, one trajectory. Okay. To create that, because I put the camera on top, okay, this is like 6 meters. I need to go up on the roof of the pedestrian alley, okay, and then install that camera. Okay, so we can see this. Yeah, this is the example of screenshot. A few seconds. Okay, and this is the example of observation number, and then this is the person number. That means the ID. Yeah, and the ID, and then this is the time, represent the time frame. In 1 second is 30 frames, because we are using camera, and these are the 2D coordinate. Now the 2D coordinate is actually put it into the actual coordinate on the from the camera. I need to convert it to the actual coordinate in the field. Yes, yeah, we can. There are a lot of methods, but I'm using very simple linear regression, yeah, method. You can still find the paper of this, yeah, in 2000 or 2000, yeah, maybe. So another technique is you can track the car trajectory. Yeah, this is the study, my study. Yeah, when I was in Ateneo with Toyota. Yeah, we want to get the potential car accident in its intersection. Okay, so we track the car movement. So each line here, each color represent one ID. Can you see that? Okay, so using camera as sensing device, we can actually track trajectory of vehicles on the road. Yeah, the simplest thing is you want to know how many is turning left, turning right, and so on. So this is easy to get from trajectory. Okay. And again, this is in Ateneo. Yeah, this is me. Yeah. So I put the students there. Yeah. Volunteer. This one is like 200 students volunteer in one activity time. Okay. So we do pedestrian experiments in the campus. Okay. So I asked them to walk, but in order to track them, okay, at that time my capability was still very bad, so I tracked them based on the hat. Okay, so that I can track them easily, and I give them red hat, then we can track them easily, so we can get the actual movement. Yeah, so what will happen if the become narrower, become wider, they have certain restrictions. So we can have a lot of pedestrian experiments. Yeah, interesting. Yeah. So the same thing, yeah. Using trajectory, we can track also the price in the stock market, isn't it? Yeah. So if you or the volume, yeah, or any trading indicator that you want. Okay. So this is example of movement of price and volume. And so you change the variables. When we say space, that's space is feature space in this case. Yeah, not necessarily 3D space physical. It can be price only, can be price with volume, can be all this open, close, low, high, and so on. So I also taught how to become quant. Yeah, so meaning quantitative trading simulation. Totally different from urban planning, I understand. But the same technique, yeah, we can apply for many different fields. That's the main point. Okay, so you can track your activities, so the agent is you. Okay, and then the schedule represent the nodes that you want to track. Okay, these are another examples of how we apply trajectory in many different fields in our life. Yeah. So the node can be nominal, not necessarily numerical. Yeah. So and from the pedestrian studies, so we also find from the trajectory we can find the self-organized behavior. Yeah, this is the complex system. Yeah, but apparently in the real world, pedestrian is actually creating their own lane automatically, yeah, to reduce the collision with other pedestrians. Yeah. So they create self-organized lane formation. Okay. Now using that, you can actually easily make efficient movement, yeah, simply by putting arrow in its of this beginning. So separate them in the beginning, then they start to create different lanes. Yeah. So then the movement is more efficient. That means the traffic signal timing will be reduced, yeah, for them to cross the road. Okay. So again, it's very simple study, but you can start to see the usefulness of trajectory. Okay. And a while ago, I showed the sample of how we track the car in the intersection, yeah, for the what is this called near miss. Yeah. So we predicted the potential collision, yeah, between trajectories. So say you have this green trajectory here, okay, and then red and blue, okay, and before it happens, okay, we can project, right? So once you project it, you can see the potential collision, and then check what is the time, yeah, whether they can actually really collide or not. And then from there, you can also get more detail, yeah, about the angle, yeah, collision and potential collision angle. And so So, okay, so how about this one? How many dimension in this 3D space, physical 3D space? Yeah, I have trajectory x, n, t, and then I have 3D space x, y, z. So can you think about how many dimension here? Dimension means the number of variables.
Is it three, sir? 3 dimensions?
Actually, no, more than that. 3 is only space, isn't it? Okay, but you forget time.
Time.
Time is also dimension. So then you say maybe 4. No. Okay. The n here represent the ID. Yeah, that means the agent, right? So at least you will have 5 dimension. Okay. But there is a but here. Why? When you start to put agent, the agent ID itself, yeah, may be related with the whole database. Okay, about the age of that agent, the gender, the socioeconomic variable, their preference, their shopping behavior, and so on. So you start to see the dimension. Okay, once you have that, now depends on what data you have. Can you see that? So trajectory analysis may include so many dimensions beyond what you see. Because once you put it into ID, that ID will be related to any others. Okay, that's why we are using trajectory, very rich. Yeah, so trajectory contains so much hidden information, yet it's very simple. Yeah, it's very primitive level. Yeah, because we did not aggregate that yet. Okay, so using that primitive, you have more freedoms. Yeah, how you are going to aggregate this? Yeah, are you going to aggregate over time, over space, over path, over agents, and so on? That depends on you, right? So, is there any possible application in your area of application about trajectories? But yes, Dennis.
Sir, can it also apply to say for example land use changes from different satellite images?
Yes. Yeah. So now, if you want to get more aggregate land use changes, that means the states. So you want to change that. Okay. If you want to put it into satellite, then its pixel should represent something. No? So you need to do image segmentation and so on. Okay. And over time, then you will get the trajectories. Okay.
Yes. It's related to my thesis proposal regarding what they call this land degradation studies.
Land
Land degradation.
degradation. Okay. Yeah,
So I
that's
want to
interesting.
find out
If you
the
try to use this trajectory things, yeah, so then the way you analyze will be totally different. Okay. Why? I give you a very simple example. Every 2 nodes represent the speed. Every 3 nodes represent the acceleration. Can you see that?
yes, sir.
Oh. Then suddenly you will start to see, oh, I can get actually a difference equation or differential equation out of this. Okay, it's not just points. It's actually the much deeper mathematics. A lot of theory you can develop based on this alone. Okay. Okay, I think anything else? Any idea for your own study? Yeah, Dennis already said, I want to use it for land use. That's good. Aaron,
Thank you,
what
sir.
do you think? Yeah.
I think, sir, I can apply it in analyzing the use and accessibility of public parks and plazas. Say, for example, studying outdoor spaces or green spaces.
So how you put that into notes and trajectory?
I'm thinking, sir, if I can track the anonymized mobile data to see how long people stay in a park or which paths no they use and way they usually congregate no and then cross-reference with a certain form of data, say for example demographic data. So from the planning insights, sir, I can identify underutilized parks no to target for improvements.
Yeah. So I think that's a new way of thinking, right? Rather than just relying on questionnaire, which is
Mm-hmm.
clearly unreliable, so you get better data.
Yes, sir.
Yes. Good. How about the others? Justin, Blaze, Liam, any idea? Yes.
Either I think I can use it in my work. I work as an instructor here at our state university.
Mm-hmm.
I think maybe I can use my students as agents, and then the trajectory would be, let's say, the topics wherein they take a while to really get or to understand.
Mm-hmm.
Something like that.
That's also right. You can also apply education. Yeah? The note
Yeah.
can be for example, the score of the quiz.
Yeah, something like that. Yeah.
Yeah. In each students. Yeah.
Or for like an exam, which part did most pupils get the correct answer, or which one
Mm-hmm. Yes.
have a hard time with it? Something like that.
Yeah. So you can apply in anything, right? Once you understand the concept of trajectory, yeah, you can analyze a lot. Yeah. Yeah. Lian, please, you want to say something?
I'm still thinking where I can apply it, sir, because
Hmm.
I'm not sure if what I'm currently working on is drainage design. So that's my current work. So I'm not sure. There are other softwares already available for the flow of
Uh,
water. So
I
um
understand. If you rely on software that someone else already did, that's okay, right? For the project, yeah. But if you want to do some kind of research, something that innovative that your own, you develop on your own, then you start to need this. Yeah. But if you just want to use, yes, of course you don't need. Right. Yeah. This.
For me, my research is my personal research is about youth resilience
Hmm?
in youth resilience.
You see clear. What's that?
So I began my own thesis in about crime and trajectory of rising crime whenever there's a resettlement. Increase of population results to increase of crime incidents. So
Hmm.
it's no brainer that it increases just because of population increase, not because of the demographic.
Hmm.
But I shifted to youth resilience to make it more positive uh, because there's ethical implications for the crime. And what I'm thinking of is to have a trajectory on youth resilience,
Hmm.
specifically on how they overcome their challenges. So how well they're doing in school, uh, what kind of social support they get, and specifically, um, uh, yeah, I still trying to think about it, but uh, try to understand also like uh, how I can project their development in the future.
Okay.
Because they're also
When you want to
Like-
apply trajectory, right? When you want to apply trajectory, important to understand definition of trajectory. Yeah, trajectory means node sequence. Okay, that means you need to have node. So, say in your study, what is the node? Okay. That change over time. Okay, what is the agent? Because node sequence of the agent, right? So, what is the agent here? So once you understand, oh, this is my agent, okay, and how they change over time, okay, then you have node sequence, then you have trajectory. Okay,
Thank you.
that's how you define. Okay, as simple as that. Once you have that data, then you can analyze whatever you want. Okay, so
Thank you. Yeah, thank you for the node sequence. I think that
yes,
helps me think about the steps.
that's the definition of trajectory. A trajectory is just node sequence, isn't it? So available. Where? There. Yeah. What is trajectory? Defines of sequence of points, yeah, or node sequence, yeah, over time and space. So that means you have the agent, yeah, you have the space. That space is up to you to define, and then you have the time. Yeah, of course you have nodes. So if you can define the nodes, if you can define the agents, then you create trajectory. Okay. Once you have the trajectory, then you analyze based on trajectory method. Okay. And suddenly things different. Okay. Because now you no longer come. Okay. Okay. So let's come back to transport. Okay. So I give you two different kind of field, but let's come back to transport. So this is static trajectory, yeah, for transportation. So what is static trajectory? Yeah, so it's for an agent I, yeah, this is just projection. Yeah, projection of trajectory into the physical space dimension. Yeah, so mathematically it's a line integral. Yeah, so for example, this is my hand drawing. Okay, this is the actual trajectory, the line here. Okay. And then over time, right, different time. Okay, but because I remove the time, so I will put them into down here, the projection into the space. Yeah, in this case, 2D space. Yeah. If you have 3D, then you have 3D space. Yeah. So can you see can you understand the drawing or not? Yeah, it's just ugly drawing of sketch. Yeah. But the point is, if you have trajectory over time, okay, and you project that into the space, okay, then you get a static trajectory. That means static trajectory, you don't care about the time. You only care about the space, but the sequence represents the time. Okay, so static trajectory is of a moving agent is a projection of the dynamic trajectory onto the space dimension. Yeah, so there is no time dimension. Yeah, that is why we call it static. Yeah, so a while ago in pedestrian studies, remember, we already have that static trajectory. Yeah, actually that's the beginning. So we have the graph, okay, with this node and links, okay, and then we can create a trajectory. Can you see this notation? Okay, we have the trajectory, mean you have the first node until the last node. Say you have the origin is R and the destination is C. Okay, and then these are the node sequence. Yeah, so V1, V2, V3 until Vk. Yeah, the V in here represent the nodes. Yeah, so there is no time dimension. That's why we call it static. So this represents steady state. Yeah, this is before I have n. Okay, so the steady state assumption telling that, look at this, I observe the flow that does not change over time. Yeah, meaning the network is actually in equilibrium. Yeah, so this is not applicable for the time variant system, of course. Okay, if you want to know the actual time of what time is it, so that's totally different study, which is much more complex. You know, static equilibrium and steady state is simpler. Yeah, simpler does not mean lower class, man. Can be higher class, but with that assumption, you need to know what is applicable and not applicable. Yeah. So what's the significance of that? Yeah. So given the focus, yeah, of the agent-based tracking, yeah, rather than counting, right? So this has significant potential for the ITS, right? So you can leverage the modern tracking technology, GPS, mobile phone, computer vision, and so on. Yeah. So trajectory analysis is much better and much more modern, yeah, oriented than counting. Yeah. If you still do counting, click, 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 click on the street, yeah. So that's old-fashioned way. Yeah. For small studies, fine, but why you still rely on 1960s technology then when you are already in 2025 with AI is already around for 3 years, right? So this will allow more granular, yeah, real-time understanding of the traffic flow, the OD pair, and then what is the alternative flow, yeah? What is the substitute flow? So, and then you will be able to track the real-time trajectory, yeah, about what is the connection between the flow F, the OD, and then the alternative flow, yeah, T here, and then S here is the substitute flow. Yeah. How you will adapt to the condition, the changing condition in the actual road. Yeah. Even though the computation is static, yeah, but once you project it and then you chunk the time, okay, so within that time period is static. That's the assumption. Can you understand that? Okay. Within, for example, within 15 minutes, I consider it as static, or within 5 minutes, I consider it as static. So in overall, still dynamic. Anyway, when you do real counting, yeah, it's the same thing, right? You assume 15 minutes, right, of the counting of the flow. So that's exactly the same method, yeah. So this one was already done a while ago. So I will just skip this part. Yeah, we use the same technique here. Now, I have 5 trajectories, and I have the graph like this. My question is, can you assign the trajectory ID into this graph? Okay. So, can you get what is called flow set? Flow set is instead of flow, I want to get the ID of each link, yeah, of the trajectory in its link. I want to get the ID in its link, ID of the trajectory. Is it okay or not? So this is the example of the answer. Okay. So I have here A, B, C, D, G, H, right? So number 1. So can you see this? A to B, right? Every 2 I put here. So that one I put number 1 here. Can you see this? This is the flow set. Okay. From A to B, then go to C. So in that case, going up. See, number 1 in here. This is the flow set, mean the ID number 1 going up, not going down, going up. And then from there going to D, there. I track, can you see this? The flow set represents the tracking ID. Okay. Yeah. From the tracking ID, the flow set, can you get the flow? Easy. Can you see? How many flow here? 1, 2, 3, 4, 5. Then you put it here, 5. Is it clear or not? Next question. How many is the OD from A to H? From A to H. How to 5, of course. Now, how many from A to D? 2. Yes. How do you know? You check here, the one that going out from A, and then you check here the one that going into D. Okay? And then you take overlapping between the overlapping intersection between the two sets. The number of that is the actual ID of the one that get OD. Eh? Interesting now. Yes, Lian, you want to ask something? Any question?
Hello?
Yes.
Hello? Can you
Yes,
hear me,
yes.
sir?
Yes.
Yes. I just wanted to ask if the flow from B to E isn't the number 3 should be included there.
3. Oh yeah, that's correct. So it must be mistake because I do it manually. Yeah, that's correct.
Thank you, sir.
This must be 3. Yeah. Yeah, correct. This one must be 3. Otherwise, how can go up here, right? Yeah, thank you, Dan, for the correction. Yeah. So from there, oh, so how many going from A to D in that case? 3, yeah, not 2, okay? So 1, 4, and 3, isn't it? Yeah, because going out is 5, going in is 3, but are they actually going from there? How about this one? From C to F, is there any? Why none? Going out of C is 1, 4, going into F is 2, 5. There is no intersection. So you know there is no OD from C to F. Yeah. Huh? So how about from B to D? Going out of B is 2, 5, 3. Yeah, this one Liam is correcting. And then 1, 4. Huh? How about going into D? So from B to D is actually 1, 4, and 3. That is 3 trajectories. Yeah. So intersection between going out and going in. Easy. So you want to practice? Okay. So I give you this. Can you practice? Because once you have that, okay, from trajectory, you can put it into flow set. Yeah, from flow set, you can get it into flow matrix, right? Yeah. So then you can get the actual flow matrix. Yeah. From the flow matrix, you can, from the same flow set, okay, you can also get into OD. How do you get the OD? Now you can have two type of OD. Yeah, the one that I mentioned a while ago. Okay, you can, yeah, you can actually use yeah, this is this. You can actually get the actual OD matrix, isn't it? You can also get the turning in its intersection, isn't it? How do you get the turning intersection? Any idea? link flow is just 2 nodes. Intersection means consecutive 3 nodes. Yeah, if you can get consecutive 3 nodes, I think I have it here. Example. Wait. F. There. Yeah. So we can get consecutive 3 nodes. Yeah. From this trajectory, you can get the. How do you get consecutive 3 nodes? Now become link and link here. Is it clear or not? Yeah. So from A, B, and then B, C, that means consecutive 3 nodes, right? Then you can get the turning. Yeah. Is it turning left, turning right, or going straight? Or U-turn, you can get from here. So I hope this is interesting enough to motivate you to study this. Yeah. Okay, let's practice. Yeah. Let's come back. I want you to practice maybe one of them. Okay. So I have 2 examples here. One is this one. Yeah. This one. Okay. And the other one is a little bit more complex. So can you practice this one first? Can you can you assign this 5 trajectory only? So to that flow set matrix. Okay. Is it difficult or easy? just deduce, right? Yeah. The purpose is to prove, yeah, that later on when we found the formula. Yeah. So the answer is just there in the slide. Yeah, except for this one. So I have 3 here, right? So I hope you're correct on this one. Yeah, so this is also 3. Okay. Next. So once you have the result, so this is, I have 9 trajectories. Okay. And I assign them one by one. Anyway, this is called waving section. You know, when you have U-turn or you have roundabout, okay, you always have waving section like this. Yeah? So there are some vehicle that going straight, there's vehicle that going to the other direction. Yeah. So this is called waving section in this middle. So usually what we want to know is actually how much wave. Yeah. People are changing direction. Yeah. This represent the flow that we want to know. Yeah. So once you assign this trajectory ID, right? Then you count. Yeah, so this symbol, absolute symbol represent the count. Yeah. The one with tilde here represent the matrix set, meaning the ID. Okay. So if you get the count of this, so you get exactly the flow matrix. Yeah. So flow matrix is just an aggregation of the flow set matrix. Okay, so the actual data that you need to get is actually the flow set matrix. Yeah. But the flow matrix is just an aggregation. Once you aggregate into flow matrix, you lost information. Don't forget that. Yeah. Once you have this ID, you put it into just number, how many, you lost a lot of information because you don't know anymore which direction they are going. But if you keep the flow set matrix, you still get a lot of analysis that you can do beyond flow matrix. Okay. Next, I want to introduce you with the flow pattern. Yeah. So once you have the flow matrix, so you can put them into a flow pattern that's similar to the pedestrian study a while ago. Yeah. So the thickness represent the flow or relative flow. Okay. Okay. So this is the original sketch. Yeah. So I was going to in conference in 2009. Okay, in the scratch paper. Okay, what will happen if I do this? Yeah? I just do it manually and doing the. You see the small point here are the trajectory IDs. Okay, in manual way, and then trying to draw that, and there's a problem that we cannot get the OD, but I can get this one. Yeah, this is the, I can get this one also. These are the formula that we can actually derive, yeah, from this simple matrix and ODs. Okay. What is this? The flow is equal to the OD, origin destination, multiply, this is Hadamard product multiplication of the adjacency matrix. Yeah. This is not complete formula, yeah. This is but based on only on this sample that I make only 8 numbers, yeah, and 5 trajectories only. Yeah, so we can derive a formula. Yeah. So, and eventually I got a lot in. So 1 year later, yeah, this is the scratch. So we can get a lot of formulas, yeah, out of that. The same technique. Yeah. Okay. And the one that I showed a while ago, yeah, the complete formula is this one. Yeah. So and then in 2012, yeah, published in this journal, yeah, Advanced Transportation, right? Yeah, with the help of my friend, yeah. And then okay, let's go to the actual things then. Remember when you do the pedestrian study a while ago, okay, we have adjacency matrix A, okay, and you have the shortest path distance matrix. Yeah. Now I give name P, okay, the one that you use short Warsaw a while ago. Okay, so once you know that, okay, I can just give name P. Yeah. A is just the adjacency matrix, yeah, the connectivity. Okay. Okay, let's name P minus A as E. I just give name this one because I don't know, so I give name and then check the meaning. Let's give a name external matrix. Yeah. So E is just basically P minus A. Yeah. Remember, A is adjacency matrix. That means network structure. Yeah. P is the shortest distance matrix. Yeah, it's called path matrix here. Yeah. That is also from network structure. That means if you minus the two, yeah, let's call this external matrix, they are still network structure. Okay, there is no demand, there is no trajectory. Okay? Only based on the network alone, you will know all of this. Clear, yeah? Next. Okay, let me clean up. So now this is the example of adjacency matrix. Yeah? So if you have this network, so hey, this is not strongly connected, so any network, yeah, can be weakly connected, no problem. So from A to G, yeah, so A to C, that is one, yeah, to C to E, that is one, right, and so on. Okay, so once you can get that, okay, you can from the network you can get the adjacency matrix, right, and from adjacency matrix you can draw the network. Yeah. So you can practice this if you want. Okay. If you have 4 by 4 nodes here, is it possible to get the adjacency matrix? I don't have the answer, so yeah, this should be easy, right? Last time I show you the tools that I developed. Let me find. Let me find that drawing, delete. How to? Okay, so let me find the tool that we make last time. I think ideal flow tutorial. The first lab, I think, this one. Yeah. So the first lab is about matrix and adjacency matrix. Yeah, this is the weighted adjacency matrix. So you can randomize. Okay. And for our example a while ago, this one. So how do you do this? Let me cut into there. So how are we going to draw this? So you have from A to B. Okay, so diagonal is 0, right? Diagonal is 0. Okay. And then from A to B, you have 1, right? And then from A to C, you have 1. This one is 0. And then from B, you can go to C. Again, you have 1. The other one is all 0, right? So every time you change the value here, the drawing will redraw. Okay. And then from B, I define C going to D. So I put 1 here. Okay. All the others are 0. And then from D go to A and B. Yeah. So again, I put 1 and 1. Right? So all the others are 0. So there. Oh, we get exact. Yeah. Yeah. So if you want to be exactly exact, so you can press the control button and then move the mouse here. Yeah? So using the control, so I can put like that. So the A is going up. Yeah. But still not exact. So if you want B to be up, very difficult. Yeah. It's already a completely different problem. Just drawing problem, yeah. Okay. So how to get the adjacency matrix is clear, yeah? We have the tools already. Next. Yeah, you can also create adjacency matrix from this more complicated graph. Yeah, we have 8, 5, 6, 7 nodes here and more links. Okay. Now, the point is we can use from the matrix that you have. Okay, it is probably not 0 and 1. Okay. Now I want to have a symbol, an operator. Okay, I put heart here, so that it will become binary. Yeah. So let's define this operator. If I put heart, okay, then everything that positive will become 1. Okay, otherwise become 0. Okay. So with this operator, okay, for example, yeah, this is the flow matrix. Can you see this? Yeah. So 2, 2, 2. See, if I make it into heart operator, there. Yeah. So F with heart operator here. So suddenly all become 1. Yeah. The one that positive become 1. Yeah. The 0 still 0. Do you understand the meaning of heart operator? To binarize. What's the meaning of binarize here? Look at this. From the flow matrix, if I put heart, it will become adjacency matrix. So I reduce the information, yeah. By putting heart operator, I reduce the information. I cannot go back from binarized version to the flow. Can you see? Yeah, I can only reduce the information. This is projection. Okay, that means reduce of information. Yeah. So from adjacency matrix, I can get from the flow matrix, I can get adjacency matrix, but not the other way around. Yeah. From adjacency matrix, I cannot get the flow. Clear, yeah. Next, we have path matrix. Yeah, so here is the matrix, yeah, that represent the minimum shortest path, yeah. Minimum path between the two corresponding nodes. Yeah. For example, from A to C, how many steps? Yeah, this is the number of hops. How many times it will go. So A to C is one time, right? From A to E, it will go A to C and then C to E. That means 2, right? So can you understand the meaning of this path matrix? If there is none, from A to B cannot, right? From A to B cannot, so that must mean infinity. Yeah. Only the diagonal I put it as 0. Yeah. Okay. From there, if you input this, yeah, so you get the path matrix. Okay. Is it clear, the path matrix? Clear. Okay. So I have developed the program lab for you. Okay. You go to model a lab of network structure. So you can get the fault partial automatically then. Yeah. So let's see. There. Yeah. So I will randomize the matrix here. Can you see? Yeah. And I can get the path matrix. How to get the path matrix? I just put there. Nah. You can get the float partial automatically, yeah, without I already give you the software. Yeah, for your assignment as well, yeah, you can use the same. Yeah, as long as you get the input, yeah, distance in here or flow, so you get the path matrix. So you can also get the external matrix. You can get also the binary of the external matrix, or binary of adjacency matrix. Yeah, remember the input is the adjacency matrix. Yeah, and you can binarize also. Yeah, so to communicate between different pages, so you can save and load into CSV format. Yeah, of course you can change the number of nodes. Yeah, it is complicated. Is it clear? I hope this is useful. So this is talking about network structure. Yeah, the lab is still under dev, meaning this is the under development, so not yet full. Clear? So you have the path matrix, yeah, you have the adjacency matrix and so on. Yeah, from there you can get the external matrix, yeah. So that is minus only, right? The path matrix minus the adjacency matrix, so you get the external matrix. Okay. That's the first part, yeah. Network structure is the first part. Let's go to the second part. Now you want to utilize the network, yeah. If you want to utilize the network, what do you need? You need the trajectory, yeah. So from the trajectory, what you can get? You can get the demand side, yeah. So the network structure represents the supply side, right? So now you can get a lot, yeah. You can get the flow matrix, you can get the origin destination matrix, you can get indirect flow matrix, yeah. You can get alternative flow matrix, substitute, and then turning distribution and stochastic matrix and so on. So you can get a lot from the demand side, yeah, different matrix. So let's discuss, okay, fully utilized or underutilized. Yeah. So we define fully utilized if all links, yeah, in the network get at least one trajectory, at least. Yeah. Now, otherwise, okay, we call it underutilized. How do you distinguish? Underutilized means at least one link in the network have no trajectory passing there. Okay. Now, why this is important? Because the formula, there is a formula that is actually only for fully utilized, okay? And there is also formula that is general. Okay, so for example, A had a product with F cup here, cup meaning binarized. We'll come back to F cup, yeah. F cup means binarized. So this is just simple identity, right? So of course, this one. But when it is fully utilized, okay, you will get this formula. Yeah. So A multiplied by F, and A is adjacency matrix, multiplied by the flow matrix, which is binarized flow matrix, you will get back the binarized flow matrix, which is the same as adjacency matrix, if fully utilized. If not fully utilized, meaning at least one of the link is no trajectory, that is not, it will be the same as this one, F bar, okay, but it's not the same as A. So this will become also one of the tests, yeah, whether the network is fully utilized or not. Clear, yeah? So let's take the example, yeah. So I have this trajectory and the network, okay, whether this is fully utilized or not. What you will do, yeah, you assign, yeah. You get the adjacency matrix, you get the flow matrix, and then you binarize this, right? So when you binarize this, you check, yeah, whether F binarized is the same as adjacency matrix. Oh, apparently not. Why? Because there is one link here, TA, which is not there. That means this trajectory is only 4 trajectory, does not make the network fully utilized. Yeah, still underutilized. Is it clear or not? Definition of fully utilized and underutilized. Okay, so from there you can also get utilization index, yeah, which is the value between 0 and 1. Yeah, 0 means no trajectory agent pass into the network. 1 means fully utilized. So if less than 1 means underutilized, but how much underutilized? So you can get the index, yeah. So using the same example, yeah. So the number of links 1, 2, 3, 4, 5, yeah, that has flow supposed to be 6. In that case, utilization index is only 83%, right? So this, because this is less than 1, so the network is underutilized. Is this clear? Now, from the network and the trajectory, yeah, so you can get the adjacency matrix, yeah, flow matrix, binarized flow matrix, yeah, utilization index, yeah, and then check whether this is actually underutilized or fully utilized. What is the value? Yeah, so you can practice this, okay, and put it there. So you get the flow sets. From there, you can count its elements. So for example, this one is 3 elements. So here the flow is 3 and so on. Yeah. From there, you can also binarize that. The binary is supposed to be the same as adjacency matrix. Yeah. If they are the same, then it is fully utilized. Yeah. So 100%. Yeah. If not the same, then underutilized. So you can calculate the utilization index. Is that clear? Now, from there, you can also calculate origin destination matrix. So this is one of the important point, right? You can also calculate the indirect flow matrix and alternative flow and substitute. Yeah. So what is this? I will discuss it one by one. Yeah. Okay. But I want you to understand that now I can get D here is origin destination matrix. Yeah. F is the flow matrix. That means I will get another matrix called L, which is indirect flow matrix. Why? Because F, the flow matrix is actually direct flow between 2 nodes. Yeah. But OD is represent both direct and indirect flow. Right? So in that case, if I minus the OD matrix with the flow matrix, I will get L, which is indirect flow matrix. Yeah. Now, interestingly, L itself represents the alternative route or substitute route. Yeah. So this can be divided again with into two complementary matrix, yeah, with this alternative and substitute. Yeah. So L is T and TC, that means a substitute, complementary of this. So let's define this. Direct link is a link, yeah, which is an order sequence of two adjacency nodes. While indirect link is actually a path between two order pair of nodes in the network, but there is no link connecting the order pair. So clearly F, yeah, flow matrix is aggregation trajectory of this direct link. Okay. When you have direct link, that means there is indirect link. Yeah. So indirect link is the aggregation trajectory that pass through the link that is indirect. Can you distinguish between direct and indirect link? I give you example first so that you can understand. So I have simple, yeah, from A, B, C, and D, right? So when you say direct links, A to B, that's direct link, right? B to C is direct link, correct? And then C to D, that is direct link. Okay? How about indirect link? A to C, that is indirect link. Yeah? Or A to D, yeah? That is indirect link. Or here, from B to D, that is indirect link. Is it clear or not? Yeah. Direct link is two consecutive. Indirect link is not two consecutive. Clear, yeah? So this is the link. Now, how about the flow on that? So in that case, you have two possible causes of indirect flow, right? One is, hey, I have the flow, okay, but there is no direct link between the two. The other one is, there is direct link, but there is indirect link. That's strange. Yeah. Okay. So that's why it's called complement. Okay. So one part is no direct link between two nodes. You have indirect flow, but there is no direct link. That means there is no choice but to use that indirect link. So in this case, yeah, we call this substitute road flow. Okay. What happens if there is direct link between the two nodes S and T, but the agent still prefer to use indirect link? That means alternative, right? So they can either use the flow matrix or indirect link. So remember, yeah, to make it simple, I will put indirect flow is L, consists of two parts. One is T, alternative flow, that means there is direct link, but they still use indirect. TC means there is no direct link, only indirect. Is that clear or not? So from here, we can get the flow from trajectory. A while ago that we already did this in pedestrian, so I just skipped this part, which is exactly the same. Yeah. So what is flow? So flow matrix represents the number of trajectory that pass through the corresponding link, isn't it? So you put the flow set matrix. Okay. So I put tilde here represent flow set. So if you have the trajectory, yeah, so the flow set matrix consists of ID of the trajectory. Yeah. So you have the node sequence, this is the trajectory. Okay. And then you have I and J, which is consecutive. Yeah. This is H and then H plus 1. Can you see that? So if you have two consecutive, that means this is represent the flow matrix. So the count of this flow set represent flow matrix. Okay, so the algorithm you can just look, yeah. But the point is, I have already developed from this algorithm, okay, the lab, yeah, for you. Okay, can you go to model and then go to this lab, network utilization. So you in here in this lab, all you need to do is you generate random matrix, yeah. So at any size you want, okay. Okay, and then you can generate trajectory like this, right? So just click, you will generate random trajectory. Yeah. If you don't like, you clear. Yeah. Or if you don't like to generate trajectory, you can manually input. Yeah. For example, this one, I copy, yeah, and then put it here, right? So, and then I will check if this valid trajectory or not. Yeah. Check first. If it is valid, then you will there. I copy, so I get a new trajectory. Yeah. Then what you want to get, yeah? What do you want? You want to get the direct link, indirect links, so you can get, yeah? It's already there. Easier for you. Okay, so alternative route, yeah, and substitute route, so you can get all, yeah. So I hope this tool is helping you to understand, yeah. Without this tool, what I did before is I do it manually, yeah, in a piece of paper. Yeah, it takes. That's why it takes many years, yeah, to develop, because I do it manually. Yeah, but if you have the tool, so it should be very simple. Yeah, once you put that, so you can test utilization. Oh, this is underutilized or so on. Yeah? Okay. So it will. So this one is missing in the link, so then you can add in here manually. Okay. I hope this is helpful. And then if you click this bottom, yeah, let me generate more random matrix and then generate random trajectory and test. Now, oh, still okay. I need CE and then DC. So let me get CE and then DC. Is it okay or not? Let me check this is valid or not. Oh, this is invalid. Okay, so you need to have generate a trajectory that actually valid. Right? PAE is it? So let me get more trajectories. Okay, and still underutilized. DC is not there. Okay, in that case, let's generate something with DC. Okay, so from D to C and then to E. Okay, let's do that. Okay, I will. Is this valid? Yes, it's valid. Then we add. Okay, then I test again. Oh, it's already fully utilized. Okay, so I have 15 trajectories, and then what I will do, I will show the network utilization matrix. There, I get the F, I get the D, I get the L, T, and S. It is TC, yeah, S is TC, and then I get the flow set also matrix. Oh, nice. Okay, so I hope it is everything clear. Yeah, for your assignment. Okay. So I hope this is easy enough for you. Just to input the data and then click, yeah. Okay, so then you can practice this, yeah. So once you have the network, you can practice the input and trajectory and to get the flow matrix and to get the adjacency matrix and so on, yeah. So with this, you can apply for any intelligent transport system, yeah, basically. The trajectory can from GPS, from the computer vision, or any object ID that you can get with technology. Yeah. From here, you can also calculate the stochastic matrix for a later ideal flow network, or you can get also the turning flow. Yeah. So turning flow is not there in the program, but you can calculate by yourself. Yeah. Once you have the three consecutive nodes, then you can get the turning flow set matrix. Yeah, from there, you can get the actual turning distribution in each intersection. Okay. Now, what's more interesting part is actually you can get the OD also, right? So, okay, this is the framework. Yeah. A while ago, we have adjacency matrix, and then you have path matrix. Yeah. And then if you minus, you will get external matrix, isn't it? Okay. So the interesting part here is there is a correspondence. Yeah, there is a correspondence between these matrices. Yeah, between network structure and network utilization. Okay. So from the path matrix, they are actually related to OD set. Yeah, related to OD matrix when you count. Okay. Well, the adjacency matrix is related to flow set, related to flow matrix and the flow pattern if you visualize. Now, external matrix, okay, you will have external set, and then from there, you will get L, the desired length, okay, which consists of substitute and alternative route, yeah, T and S a while ago. Yeah. So there is a parallel, okay, of interesting pattern, yeah. Parallel pattern between the path and OD. There is a parallel pattern between the adjacency and flow set and so on. So now this is not traditional OD. Yeah? The traditional OD is from O to D. Okay, from source node to the sink. Yeah? But when we have using indirect link, so this is generalized OD. Yeah. So the traditional OD is just a subset of the generalized OD. Yeah, because this source and sink is a subset. Why? Because now I define it, okay, so that from all links, from all node to all nodes. This is the OD from all node to all node, not just from the OD source and sink. Can you see the difference? Yeah. So I give you an example. So this is direct link definition, yeah, and this is indirect link definition. So you can just read by yourself. And a while ago, using that program, you can already list all direct and indirect links. So these are the things that you can try, yeah, on your own later. Yeah. Now this is the OD. Yeah. So generalized OD, yeah, is a set of trajectory that pass through node S to node T. Yeah, this is the O and T. Yeah, either directly or indirectly. Okay, so directly means a single edge. Indirectly means a path. Yeah, indirect links. So if you look at this, let's compare this with the direct. Indirect links means, can you see this? This is S, not the next one, but up. There is a other node here, and then you get the T here. Okay, so this is indirect link. There is some other node R in. Okay, so now if you put that in OD, meaning I have S here, okay, and then I have T here, and there is either one or none. So dot 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 means either directly or indirectly. Okay. So what is the importance of OD flow? Yeah, in traditional modeling transport, yeah, maybe start from next week. Yeah, in traffic assignment, OD matrix is the default input. Okay, so KIGO, yeah, garbage in, garbage out, without the real input that you have. So practically you don't have the output. Okay, and the flow matrix in traffic assignment is the output. Okay, so with that you can actually do what if analysis. Yeah, if you change the network structure, you will get the new flow, right? So the OD you assume the same, not change. Okay, so from here you start to get the from each trajectory list here, you can get the OD matrix, yeah, the direct and indirect link, and then the flow matrix. Yeah, this is the example that you can start to list down, yeah, each of them. Yeah, using that lab a while ago, you can get exactly the same values. Yeah, so you can get this OD set, and then you count, yeah, the number of elements, you will get the OD matrix. Yeah, this is generalized OD matrix. Okay, in which if you put only the sink and source basin, you will get the usual traditional OD matrix. Okay, from there you can also get the indirect flow. Yeah, L is just OD matrix minus the flow matrix. Now, what's the interpretation of that? Yeah, some indirect flow are desirable, okay, as they reflect the user preference. Yeah? Maybe they want to avoid certain road. Yeah, maybe because they perceive certain safety. Yeah, maybe dangerous to pass there, right? Or maybe some aesthetic reason, maybe more beautiful if I pass indirect road. Yeah. So, but that's also represent robustness. Yeah. So if you have redundancy in your network, okay, meaning there is an alternative route, okay, that means your network is robust. Okay, if there is a network disruption, for example, demonstration, fire, whatever, or maintenance, okay? So, or expect a flood, probably in Metro Manila, so many floods, okay? So, unexpected surge in demand will happen. Then, if you have alternative flow or substitute flow indirectly, that means your network is resilient. Yeah, without indirect links, your network become only, this is the only route. Is this clear? The interpretation meaning of this, yeah? So once you get that, so you can start to see, yeah, where is the indirect link flow, how much, yeah? Okay, based on this interpretation. Okay, so now you can also divide, yeah, the indirect link flow into two parts, yeah, alternative route and substitute, yeah, TC or S a while ago. So alternative route means it utilizing indirect link, but direct link is actually exists. Okay, substitute route means only indirect link, yeah, because there is no direct link. Yeah, so if you analyze these two, yeah, it will help you to analyze whether direct link itself is underutilized or not, right? So the symbol T represent alternative route. Yeah, so there is direct links, but agents still prefer to use indirect link. Yeah, okay. So indirect flow despite direct path. Well, symbol. Yeah, this means if you have low T, yeah, low value in the indirect flow here. That means, yeah, majority of the traffic demand using direct link. And this is expected, right? Okay. So, but that is also somehow they use indirect. Okay. So direct path is utilized efficiently, yeah, minimal detouring, yeah. But in the negative sense, yeah, that means if T is very low due to high congestion or capacity constraint in the direct link. That means also there is no viable alternative. Yeah. So there are two ways to interpret this, yeah, in the positive way or negative way. Yeah. Now, how about the other one? Substitute or S, yeah, TC or S, the same, yeah. Substitute route, that means no direct link between the two OD, yeah, S to T. So there is no choice but to use indirect link. Yeah, I want to go from S to T, but there is no other way except to all this long path. Yeah. So we can also quantify this the flow of this indirect flow. Yeah. So if you can get that, then you will see if the value of high TC or S, yeah, indicate significant indirect flow because no direct connection exists. That means there is unmet demand, isn't it, in the direct link itself. So this is an opportunity. Oh, this is the way I want to build new infrastructure. Yeah, I need to build new road and so on. So this is the indicator. Okay, but in the positive sense, yeah. In the negative sense, that's also lead to inefficiency. Yeah. So high TC or S, yeah, meaning increase in travel time, yeah, congestion on the alternative route. Yeah. This is how you interpret all of these values later. Yeah. So this is just an example how you will get. So the same network, I put the same trajectory, yeah. Then you will get alternative route links and substitute route links, yeah. So you can check in detail later, yeah. And from here you can get the matrix, yeah, the two matrices, yeah. So I get the L. From here I can divide into T and TC, yeah, or S. Okay. From originally I tried to get this is the wrong algorithm to create the OD matrix. Yeah, this is the first algorithm that I thought this is right, but this is not correct. Yeah, because of the why is this not correct? Because intersection is actually two-way, but our way of doing is actually one way, right? From O to T. So that's make it wrong. Yeah. So this is the counter example why this is wrong here. Anyway, so this is the corrected algorithm eventually. So when you create algorithm, it's not just simple. So we need to make a lot of counter example. Okay, eventually you get the correct one. Yeah. So yeah, using that simple example, I can get the correct value eventually. Yeah. So now from this is the main part. Yeah. Okay. Look at this. I can get the relationship, and this is interesting, yeah. I can get the relationship between flow matrix, NOD, and adjacency matrix, and alternative flow. Yeah. But look at it. I can just add the flow matrix and the alternative. Remember, the alternative means there is direct link, but there is also alternative. Yeah, they are using alternative even though there is direct link. So this is adjacency matrix. This dot represent Hadaman product. That means element by element multiplication. Okay, and D here is the OD matrix. Okay. Yeah. So what happened? What's the meaning of this? Oh, I got the formula at first, yeah. I got the formula. I can get mathematically simple from OD matrix to flow matrix, isn't it? Yes. But be careful. This is Hadamard product. Okay. So Hadamard product means multiply by the adjacency matrix. That means you reduce the information. Okay. If you know the OD matrix, yes, you can get the flow matrix. But if you know the flow matrix only and adjacency matrix only, these three only, you cannot get back the OD matrix. This is the the meaning of this formula. So this is bad. Yeah, this is only one way formula. You see this? Okay, from OD matrix, okay, you can get the flow. Yeah, but you cannot get back the OD matrix. Why? Because this is Hartman product. That means you multiply with the adjacency matrix. So you lost information. Okay, mathematically. Yeah, there are many ways to estimate OD matrix from the flow, of course. Yeah. So with this, okay, I will introduce one last. Yeah, the lab. The last lab, which is related to your is the relationship between a network structure and utilization. Yeah, it's exactly the same like before. Okay, so you create random matrix and you generate random trajectory. Yeah, and you can test the utilization also. Okay, and then you can test the relationship here. This is the make it difference. So which one is true, which one is not true? Yeah, this is exactly your assignment. Yeah. Yeah, you can also show the matrices, yeah, to check whether they are correct or not. Okay. So with that, I guess this lesson is done. Yeah. So I hope you enjoy. Yeah. So what did you learn today? Yeah. So you can get the actual relationship, yeah, between network structure and network utilization. Very general, not necessarily strongly connected. Okay. If your network is acyclic network, so you only have this one, no alternative route, right? So this is simpler. Yeah. So if you have, and there are many other relationship there, yeah, that you can also check. For example, this one. Right? So, okay, so the potential application you can check, read by yourself, yeah. So you can actually visualize and do a lot of early warning system, for example, yeah, on the ITS, yeah. So, right. So I show you the algorithm, I show you the linear algebra, yeah, simple connection between network structure and network utilization. Yeah, everything is based on trajectory. So with this, I hope you can start to appreciate, yeah, the more modern approach, yeah, to go to the research part and development of new kind of transport method. Yeah, many of you are master and PhDs, right? So that is expected. Yeah, if you just use the software, that is undergrad, right? Okay, so you need to enhance your level. Yeah, go beyond just user. You're supposed to develop. That's the expectation of master and PhD level. Okay, with this, thank you very much. So if you have any feedback, so give me, and I will wait for your actual feedback. Is everything clear? Anything not clear? Okay, so thank you very much if you have no feedback. So check your own midterm. Yeah, there is a feedback there so that you can see why you get very high. I think a few of you get very high grade. Yeah, Lian, I think you get very high grade. Right? Yes. Okay, so see you next week with what is the topic? Next week you can check in Moodle. I think is the traditional transport demand analysis, yeah? Trip generation, trip distribution, and so on. Yeah, you can study before a class so that you can get better understanding. Yeah. Thank you. And
Thank you,
see
Prof.
Sir.
Thank you,
Yes,
sir.
sir.